So welcome to mini-course 05. It should be taught by Professor Ville, but unfortunately he got sick. He did not show up for the conference last week, and he's not going to be able to deliver the mini-course this week. In his place, we have Professor Elcio Hollande from the Department of Mechanical Engineering from the Federal University of Rio de Janeiro, and he's going to deliver the same mini-course, the use of techniques within the Bayesian framework of statistics for the solution of inverse problems. Please, Professor Elcio.
Oh, good afternoon. Thank you very much, Antonio, for the introduction. I actually really, when you said that the same mini course is going to be given by me, I'm not sure about this because I really regret that Ville could not come because actually we started working with the solution of inverse problems within the Bayesian framework about 10 years ago when Jari Kaipo and Ville Kolehmainen, they spent about 1 month with us, and they gave a very nice course, and that's when we actually liked the idea of working within the Bayesian framework for the solution of inverse problems, and then we started applying this for many problems within the last 10 years. And so it's I really regret that both Ville and Kaipo could not come. This is the outline of the course. I'm going to make a brief introduction, talk about general considerations, and present the solution of the idea of solving inverse problems within the Bayesian framework. Talk a little bit about one maximum posterior objective function. Then talk about the Markov chain Monte Carlo methods and some practical issues related to this method. And as any Monte Carlo method, it's very time consuming. And so at the end, I hope that I can talk about the reduction of the computational time for these methods. At least 2 techniques which are very well known, and we have applied them in the past, and they work very well. I also apologize that tomorrow afternoon I cannot be here because I have a commitment. I expected that Ville would be here. And so I'd like to propose that instead of finishing at 4 p.m., maybe we go ahead a little bit if it's okay for you, and then we have today and Wednesday, okay? If you don't mind, okay? Okay. So first, actually, this course is more or less centered on inverse heat transfer because this has been our main subject of research, and we are in the heat transfer laboratory at the Federal University of Rio de Janeiro. Okay. So, like inverse heat transfer problems, they deal with the estimation of parameters or functions that appear in the mathematical formulation of physical processes in thermal sciences. And how do we do this? By measuring some response of the system that we are interested in, for example, by taking temperature measurements or by taking heat flux measurements, measurements of radiation intensities, etc. Okay. And this term Bayesian, it's usually refer to techniques that fall within this framework of statistics that was developed by Thomas Bayes. Thomas Bayes was a Presbyterian minister, And actually, his main paper, it was published after his death. You know, he died in 1761, and his paper was published by one of his friends, you know, in 1763. So although what we know today, we consider today as being Bayes' theorem, it's actually attributed to Laplace. And this term Bayesian, it was actually first used by Fisher, who was Bayes' major rival, intellectual rival. And this was used in a pejorative way about 120 years after Bayes' death. And actually Fisher's framework of statistics is what we consider as like being the frequentist approach, frequentist framework, in which you actually take into account the physical model, you take into account the measurements, and you try, for example, to make statistical inference through the maximization of the frequency that happens for the measurements that you have. Okay, and so Fisher's theory relies only on the measured data, on the modeling of their uncertainty, and in this modeling, the formulation, the mathematical formulation of the physical problem goes into this modeling of the measured data. Okay. On the other hand, within the Bayesian framework, we also give credit to any kind of information that we might know before the measurements are taken. So this is called a prior information, and this prior information, it has to be coded in terms of some statistical distribution. But and this may come might come in some quantitative way, but this might also only be some qualitative information. And this qualitative information, we have to code this to mathematically translate this into some statistical distribution. And this previous information, actually, it as we are going to see with a very simple example, this actually regularize the solution. So the regularization within the Bayesian framework for the solution of inverse problems comes from the prior. But on the other hand, the prior introduces a bias in the estimates. So usually we have to spend a lot of time thinking about how to code this prior information. And another important point is that many times we don't consider the solution of the inverse problem in terms of a statistical inference, even if we work in the frequentist approach. Because many times you define your objective function in terms of not taking into account the experimental uncertainties. So you actually, and this does not allow you afterwards to take, to get estimates not only about the unknown parameters of your formulation, but also about the uncertainties related to those unknowns. For example, like the variances, if you consider approximatives as a Gaussian distribution or some other distribution. Okay. So this is already something a little bit different from what we have seen the last week, because even if we consider the solution of the inverse problem within the frequentist framework, the definition of the objective function is related to the measurement errors, to the model of the measurement errors. Okay, and so we can actually we can actually solve the inverse problem in terms of statistical inference. And usually, when we solve the inverse problem, when we think about, we reformulated the inverse problem in terms of the minimization of some objective function, we get some point estimate for the parameters. But within by doing statistical inference, we can not only get these point estimates, but actually compute other statistics of our estimates. That's one good point of this. Okay, and the major source for the solution of inverse problems within Bayesian framework is the book of, in my opinion, is the book of Kaipo and Sommersaller. It's a very complete, very self-contained book, and which actually many times when we think about doing something and we look and it's there in their book. And but also, let me mention also that of course there are many other books about the fundamentals of Bayesian statistics, but there is a very good book by Gammerman, Danny Gammerman and Roberto Lopes that is related to the computational aspects, to the practical aspects of Markov chain Monte Carlo methods, and which is basically the method that we would like to discuss with you and present to you in this course, and other the solution of other kinds of problems within the statistical framework, for example, by the solution of state estimation problems by using Bayesian filter. It's not going to be covered in this course, but it's going to be covered in another course that starts on Wednesday afternoon. Okay, Wednesday morning, where we are going to see the solution of state estimation problems via the Kalman filter and also the particle filter. Okay, so for the sake of establishing some nomenclature here, P is our vector of parameters. Okay, so we have any parameters, and these parameters can be, for example, constants that appear in the formulation of the problem, but can also represent parameters that represent a function in terms of known basis functions that we can establish. For example, we can time-dependent function, we can approximate it in terms of n basis functions, and then the parameters become like the projection of this of our function into this finite dimensional space with any of dimension n here. Okay. For example, if we have we might have some very general functions, even like this door function, where the value of the parameter represents the value of the function inside some time interval here. And other kinds of discretization also allows for this. For example, spatial discretizations. As we saw last week, many problems related to the estimation of the conductivity within the medium, and you can discretize the medium, and within each volume, each element inside your medium, you can have a constant value of the function that represents, that's actually given by those parameters. So in other words, we are actually discretizing the problem before we solve the inverse problem. And let's consider that y is our vector of measurements, okay? So the vector of measurements the notation that I use here, this is like time-dependent variables, but this, for each of those vectors here, they may contain they may contain measurements of, let's say, M sensors. So we can have different sensors that even measure different physical quantities, and they are taken at specifically at each time, and the time varies from index 1 to I, okay? And M is the number of sensors, okay? Okay, so if we make some hypothesis here that, let's say that the experimental errors of our measurements related to our measurements, they are additive with zero mean, and they have a Gaussian distribution. So by an additive error, we can write the measurement as some, let's say, exact measurement, and plus the error here, and by assuming that it's Gaussian distributed, this vector epsilon has a Gaussian distribution. Let's assume also that we know the covariance matrix of the measurements. And let's assume that there are no measurements in the dependent variables, and the measurement errors, they are independent of the parameters P. So this representation here, this T of P, it would actually come from the solution. We are assuming here that this would be our exact measurement. So this would be like the most accurate solution of the mathematical formulation of our physical problem. Okay. So it should be recognized that we are actually considering here that the mathematical formulation of the problem supposedly perfectly represents the real world. Okay? And if it does not, we can always find this a posteriori. Okay? And then we can iteratively, come back and forth and actually improve the formulation and the solution of this problem here. And also, if time allows, on Wednesday, we shall see how we can work with reduced models. Okay. Okay. So if we take this hypothesis into account, the likelihood, the statistical distribution of the measurement errors of epsilon is given by this expression. Here, y minus t is actually epsilon, right? And so when we substitute this in like this, when we substitute epsilon by y minus t, we recognize that this is actually the statistical distribution of the measurements given the parameters p. Of course, with the formulation of the problem that is given by t of p. Okay. And which is what is called a likelihood function. So in this case, with those hypotheses, our likelihood function is Gaussian. Okay. Well, of course, we could have other distributions, and in engineering, it's kind of for many applications, not all of them. Of course, we have seen some. During the mini course of Professor Uriashi, we saw here like how to deal with scarce data when you don't have many experimental measurements. And so these are very special situations that sometimes we have to go through. But many times we can get, we can propose, we can model our measurement errors in terms of some statistical distribution by the calibration of the sensors, by comparing the measurements of our sensors with some exact measurements or some very accurate measurements obtained, for example, with sensors that can be traced to a National Institute of Metrology, which here in Brazil is in Metro. Okay. So from the calibration of our sensors, we can get the likelihood function. And again, we saw this morning the course by Professor Philippe Lemasson, where he was talking a lot about exactly about how the measurements, how there are about the errors that are here inside this T of P. Okay. So many times we have to improve this model. We start with some model and we have to change it, but this, as I said, we can do this a posteriori. Okay, so if we have a likelihood function in terms of this Gaussian distribution, one possible solution for the inverse problem, which is estimating the parameters P with the measurements Y, is to maximize this likelihood function. So it's get a point estimate that maximizes this likelihood function, and this can be obtained by minimizing the term inside the exponent. Since W is the covariance of the matrix, it's covariance matrix of the measurement, so it's known before we solve the problem. I mean, it's modeled before we solve we try to solve the inverse problem, and D is the total number of measurements. Okay, and then we get this objective function, and which we call a maximum likelihood objective function, which in this case is a Gaussian likelihood. Okay, so instead of to maximize the likelihood, we minimize this objective function. And W is the covariance matrix of the measurements, and if we still make some hypothesis that the measurements are uncorrelated, okay, so the elements of the diagonal are zero, okay, and if we still assume that we have a constant variance, okay, so all the variances are equal to sigma square, okay, then the minimization of the maximum likelihood objective function is equivalent to the minimization of this objective function, which is least squares. Okay. So the point that I'm trying to make is that to consider least squares as in terms of the solution of the inverse problem in terms of least squares as statistical inference, there are a lot of hypotheses that need to be satisfied. Okay, so the measurement errors they have to be Gaussian with zero mean, and a Gaussian with zero mean, additive Gaussian with zero mean. The measurements need to be uncorrelated, and the variance must be constant. Okay. Okay. So actually, you can also when we think about the solution of inverse problems in terms of penalized objective functions, like Tikhonov's regularization, based either on this objective function or this one here that comes from least squares, it's not a Bayesian estimation. Okay, so we can because we are only taking into account the information about the measurements. Okay, and we are in some sense forcing with the penalization term that we get smooth solutions. And as we have seen how there are different ways of choosing the regularization parameter, and this has been very much discussed last week. Okay, and why is that? Because within the Bayesian framework, we are interested in the making statistical inference on what is called the posterior probability density. Okay, so while within the classical approach for the solution of inverse problems, you only take into account the model for the measurement errors. Okay, in the Bayesian framework, we also take into account the prior information that we might have for the unknown parameters. Okay, so for the solution of the inverse problems within the Bayesian framework, it can be summarized in those basic steps. Okay. First of all, we consider that all variables that appear in the mathematical formulation of the physical problem, they are actually random variables. Okay. And then our first task is to select a probability distribution function that represents this prior information, which is the information that we have about the parameters before the measurements are taken. Okay. And this you have to give a lot of thought about how to do this. Okay. Okay. So the next step was the selection of the likelihood function, which is our model for the measurement errors. Okay. So we have seen before a Gaussian likelihood, but the Gaussian likelihood might not be Gaussian. Fortunately for us in heat transfer, when we calibrate temperature sensors, and I'm even going to show you an example. They are usually Gaussian, but you have to be very careful with this depending on the kind of measurement that you have available. Okay? But the likelihood, remember that it actually represents, it's a statistical representation of your measurement errors. And with these two distributions, the prior and the likelihood, then we have to develop methods to explore what is called the posterior density function. Okay? And the posterior density function is the conditional probability of the parameters P given the measurements Y. Okay? So before we were looking at the likelihood, which is the conditional probability of the measurements Y given the parameters P. Okay? Now we are going to adjoin the information provided by the prior, okay, with the likelihood to obtain what is called this posterior probability function, and then we are going to try to get information on this is a crucial point, and it's how to get information from out of this posterior probability function, because many times we don't know it exactly. Okay, we don't know it exactly because many times we cannot get an analytical posterior. Okay. Okay, so some basic theorem statistics that the joint probability of P and Y is the probability of P given Y multiplied by the probability of Y. Remember that the P are our parameters and Y are our measurements, okay? And the denominator here is actually plays the role of a normalizing constant, so it's actually the integral of the joint probability of P and Y in the parameter space, okay? Since this is usually not known, but we can also write this joint probability in terms of the probability of Y given P multiplied by the probability of P. Okay, and when we substitute this here, we get what's called Bayes theorem, which is this expression. Okay, so we get that the posterior, which is the conditional probability of P given Y, is equal to the likelihood multiplied by the prior and divided by that normalizing constant, which is this integral here. Okay, and then and remember that the likelihood is the probability of Y given the parameters P. Okay, and many times we don't know, and it's actually this is kind of difficult to compute this denominator here. Because this integral, perform this integral in n space parameter, and so many times we simply write the Bayes Bayes theorem in terms as like this, okay? We say that the posterior is proportional to the prior multiplied by the likelihood, okay? And that's our starting point. So before we were working only with the likelihood, and now we want to make inference on this distribution here, okay? Which is the posterior distribution. Okay, so one example, one very simple example where the posterior is analytical, okay? We make the same hypothesis before, okay? So that we can write the likelihood function in terms of this Gaussian distribution. But let's also assume that we can represent our parameters in terms of a Gaussian distribution, okay? A Gaussian distribution that has some mean mu and some covariance matrix V, okay? And how is that? You have some information about the parameters, okay? And this information might be very accurate. And in this case, you have small variance for the parameters or for a group of parameters, but this might not be very accurate. And you are modeling the prior in terms of this Gaussian distribution, but with large variances. Okay, and many times this is difficult to do. You know, I can imagine people like the continuation of this thematic program that people have these problems in economics and also, for example, in biology and. But for us in engineering, many times we like the parameters, for example, thermal conductivity value. Okay, and you know that thermal conductivity is positive, and you know, for example, in practical means the maximum value of thermal conductivity of materials found in nature or even man-made materials. Okay, so. In engineering, many times it's not that difficult to propose a prior, although you have to think a lot about it. Okay, because the worst of the world is like the worst condition is that you don't have you don't know the prior information, the information that you don't, that you know for the prior, the information that you know for the parameters, and you want to code this in terms of the prior, okay? Many times you cannot give too much credit for it, okay? And so a very bad thing is if you cannot give credit to that prior information, but you give credit to that prior information. Okay, so let's assume then that we have this Gaussian distribution. Here, remember that n is the number of parameters, so the Gaussian distribution is represented in terms of this mean mu, the covariance matrix V. We have the likelihood, which is also Gaussian, and when we substitute the likelihood and the prior into Bayes' theorem, and then we take the log, we get this expression. Okay, where this last term here is given by this expression here at the bottom. Okay, so what appears here is D is the number of measurements, N is the number of parameters, W, which is the covariance matrix of the measurements, V is the covariance matrix of the prior, and so all those quantities here, they are somehow known. Okay, of course you might have to play with with your experiment. You might need to optimize your experiment and to get the most significant measurements. And when you do this and you do the calibration of the measurements, you get the matrix W. Okay, but these are known quantities except this last term, which is given by this expression here. Okay, and so one possible solution for the problem, okay, is to get a point estimate for the parameters P that maximize this posterior distribution. Okay, that maximize this posterior distribution. In this case, we have to minimize this objective function. Okay, and this is usually called the maximum posterior objective function, which in this case, this very simple case that I'm presenting here, it's a Gaussian. This posterior objective, maximum posterior objective function, comes from a Gaussian prior and from a Gaussian likelihood. Okay, this could be different. Okay, but we might be able to get some analytic form for our posterior, like in this case. Okay, so now we can see here the contributions of the likelihood, which is exactly what we had before here. Okay, it's exactly what we had before. But now in our objective function, we also have the contribution of the prior. Okay, we have the contribution of the prior. So the prior, it actually appears as a penalization term for your likelihood. Okay, so although I'm not proving anything here, I'm only presenting a very simple example, but it's clear that the prior, it plays the role, for example, of Tikhonov's regularization. Actually, the regularization, it comes out from the prior. Okay. No, it's not. It's not because the Gaussian, with the Gaussian distribution, you're favoring parameters that are around this mean mu. Okay, so this is actually a very important point, because by the same it's clear now that the prior, okay, it provides the regularization, but regularization also always introduces some bias. And so this means that if we take the expected value, let's say for a linear problem, and you take the expected value of the parameters p obtained with this objective function, they are not going to be the real parameter values as the unbiased least squares, but it's going to be mu. Okay, it's going to be mu. So this is a very critical point. That's why, and of course, this effect will be stronger when the variances are small, because you're actually inverting here the covariance matrix. Okay, so that's why I'm saying that you have to put a lot of thoughts on prescribing the prior before you start the solution of the problem. Because if you cannot trust on the information that you have, this should be reflected in the covariance matrix here. Okay. Why? Because let's say that we have one case with two parameters. Okay. Okay. And what is happening there? No? So if we have, let's say that this is the objective function, and if we have something, even like a nonlinear case, okay, that we can get something like this, okay. Okay. If we prescribe our priors, okay, with a mean mu in terms of some point here or here, we are going to get a point here or here on the other minimum. Okay, because we the prior introduce some bias, which sometimes is very convenient. Sometimes it's very convenient because let's say that we have some linear dependent parameters. Okay, let's say that this is S, P1, P2. And let's say that we have some linear dependent parameters that, okay, we have something like this, okay? Perfectly correlated parameters, Okay. So in the classical approach for this problem, when we compute the sensitivity coefficients and they are correlated like this, what we usually do is like fixing one of the parameters, right? You have to fix one of the parameters. And let's say that you fix P1. And then you do the solution for your problem and you estimate P2, okay? But many times, for example, you fix one of the parameters, let's say from another example, another experiment. And when you do another experiment, you actually don't have a deterministic value for that parameter, but you have that parameter represented in terms of some mean value and some uncertainty associated with it, okay? So if we can represent this as Gaussian, okay, we're actually here getting this Gaussian distribution, okay? And this is going to influence the parameters that we are going, the values of the parameters that we are going to estimate for P2, okay? So this approach is very convenient because we can fix the parameters, but not the parameters that we judge as known. We can fix it, but not exactly, not deterministically, but we can fix it in terms of some statistical distribution, which in this example is given by a Gaussian distribution. Okay. Then, if we like take the gradient of this objective function, if we have a linear problem, so the response is equal to the sensitivity matrix multiplied by the parameters, we get this closed form expression. And if we do Newton-Gauss, we approximate T of P in terms of some point, estimation that we have for the solution at iteration pk here, and then we get this iterative procedure where we can see that actually the effect of the covariance matrix is like the effect of Tikhonov's. Again, we can see that it's like the effect of Tikhonov's regularization, because when this matrix when we have small variances, here, we actually increase the conditional number of our model matrix here, given by the information matrix here, J transpose W minus 1J. And we can all, and for the linear case, we can show that the covariance matrix of the estimated parameters P is given by this expression here. Okay, so actually with the prior information, we also reduce the uncertainties associated with our posterior, with the parameters obtained with the maximization of the posterior distribution. Okay. This is only possible, okay? We can only do this. We can only get this expression if we make all the statistical hypotheses that we made before, that we have a Gaussian distribution for the likelihood and a Gaussian distribution for the prior. Okay, otherwise we don't get a beautiful expression like this, which is the exact covariance matrix for the linear case, and we can use it approximately for the nonlinear problems. And here is one example that is a thermal tomography, where we have a two-dimensional medium, okay? And in this two-dimensional medium, we have two inclusions, okay? And these two inclusions, they actually represent different. They represent thermophysical properties different from the base material. And in this case, what we are calling here thermal tomography, we hit. We have electrical resistances around the the external surface, okay, and also some temperature measurements taken between the electrical resistance. So we do a sequential heating of this body by turning on and off each electrical resistance, and then we measure the temperatures at some selected points for the solution in terms of an inverse problem for the estimation of two physical properties, thermal conductivity and volumetric heat capacity, and these are the results that we obtain. Okay, so we can get some quite good estimations of the inclusions inside the domain. Okay, this was obtained with simulated experiments, but one student there in Kuopio, he has also did the experiments for this case. Okay. Okay. So before we were dealing with the we were estimating the parameters by the maximization of the posterior distribution. Okay. But there would be other possibilities of computing other statistics. Okay, for example, the conditional mean. The conditional mean of the parameters, it's the integral in the parameter space of the parameters multiplied by the posterior. Okay. And this is something that we might want. Okay, and this, while for the when we only work with the likelihood, while this is only a function of the likelihood, now we have both the information here inside the posterior given by the likelihood and also by the prior. Okay, but computing this integral is might be numerically intractable depending on the size of the parameter space n. Okay, so we need to find some way out of this to compute this conditional mean. Okay, and also another, for example, we can do Monte Carlo integration. Okay. So if we do Monte Carlo integration, this integral is approximately given by the average of the samples taken out of this posterior distribution. Okay. And in accordance with the law of large numbers, when we increase n here, then we get a better approximation for these the expected values of p. Okay. So the question is exactly how do we get samples out of this distribution, because we don't know this distribution exactly. Remember that we don't know this denominator, and this denominator, it actually comes from an integral more or less like the one that we have seen before in this n-dimensional space. And this is how those Markov chain Monte Carlo methods come into picture, because they are used to get samples that are from this posterior distribution, okay, which is known exactly except for the denominator, okay, the normalizing constant. It's normalizing constant. Okay. And so the idea is that by drawing samples of this posterior probability, then we can make any statistical inference. We make statistical inference out of these samples by computing any statistics we want. We can compute like the expected value with the mean of the samples. We can compute the minimum, maximum, median, whatever we want. Okay. But as long we still have a problem, that is how to obtain the samples of this posterior probability. But fortunately, some people had these the very efficient algorithms in the past that can do this. For example, the Metropolis-Hastings algorithm and also the Gibbs sampler. So they are Monte Carlo methods which are built over Markov chains. And we don't have much experience with the Gibbs sampler, but we have very good results with the Metropolis-Hastings algorithm. Okay. But as any Monte Carlo method, they are very time-consuming, and being very time-consuming, sometimes we have to work with reduced models. Okay. But again, when we work with reduced models, they modeling errors. I mean, the errors between a complete model that supposedly perfectly represents our physical problem, okay, and a reduced model, they can be very conveniently taken into account within the Bayesian framework and by using this Metropolis-Hastings algorithm. Okay. So before I thought that here I had some. Okay, just as a small remark here, this Metropolis-Hastings algorithm it was first proposed by this group of authors, okay, but only the first one became famous. Actually, there is another author here. Only this one really became famous, Metropolis, and if in a paper published in the Journal of Chemical Physics, and you see it's not a paper on statistics, but it's a paper on applied statistics, on statistical mechanics. They wanted to derive coefficients for the equation of states by means of a statistical procedure. You know? See, by Monte Carlo integration. And this is exactly the same. Okay. Yeah. Hastings is in. I was going to mention about Hastings right now. Hastings is his paper is from the 70s. Okay, and this was really a paper on statistics. You see, it comes from Biometrica. And he mentions here the algorithm of Metropolis et al. See? And so this was really a paper on statistics, which ended up being more or less the same algorithm that they preconized there in the 50s. Okay, in the 50s, and that's why it's called the Metropolis-Hastings algorithm. Okay, and this algorithm is exactly the same one that, for example, people who work on optimization use in this simulated annealing. Okay, simulated annealing is basically the same stuff. Okay, so what I find really interesting is that see, these people, they were not thinking about inverse problems. They were not thinking about optimization. They were really trying to get equation of state is how you relate to thermodynamic variables. For example, pressure, temperature, specific density, you know. So problem have learned about. You remember this equation of state of ideal gases. Okay, like P equal rho RT. Okay, so this is one of equation of state that is suitable for a perfect gas. But how do you do for real gases? How do you do, for example, for liquids? And that's what they were interested in. Okay, so it was a paper on statistical mechanics. It had nothing to do with I mean, they were using statistical tools, but they were not really thinking about the statistics only. You know. I really don't know, Antonio. Don't know. Yes. So I guess yes, that like for example, people could have applied their algorithm, for example, for deriving the coefficients of equations of states for different materials, for different liquids, for different gases and different pressures. People might have done that, but I'm not sure. And then Hastings actually kind of in a formal way derived more or less the same method. And this is more or less the same story as Levenberg and Marquardt, right? Levenberg's paper is from the 50s too, and Marquardt's paper is from the 70s. And they actually, Levenberg and Marquardt, I think it's more interesting because they took a completely different approach for getting at the end on the same algorithm, right? Same algorithm. Okay, so and this is this algorithm. Okay, it's implemented over a Markov chain. Okay, a Markov chain. So just very briefly, remembering what is a Markov chain, it's a stochastic process that given the present state, the future state, and the past state, they are independent. Okay, so it's a stochastic process that satisfies this property here. Okay, so given this state, the state, the parameters at state t+1, this index, although it looks like time, okay, they actually represent the states of the Markov chain. Okay, so the parameters at state t+1, the probability of having this parameter at state t+1 being equal to y given the previous values of the parameters, the values of the parameters at previous states, this is equal to the probability of the parameter at state t+1 being equal to y, given only the parameter at state t being equal to x. Okay, so all this history here, it's lost, or it's actually it can be thought of that this is all inside this this last state of the Markov chain. Okay. Okay. So some definitions, we say that this distribution P star is a stationary distribution. If the chain, once the chain is in P star, it stays in this distribution. Okay. And and if P star, okay, is okay, so now if we suppose that P of t tends to P star when t tends to infinity for any P0, so for any starting point of the chain, okay, then we say that that P star is the equilibrium distribution of the Markov chain, and we also say that the chain is ergodic. Okay. And now another definition. Let's say that we consider that the sequence of states from x to y, okay, which is given by those intermediate states here, okay. Which means that the probability of moving from x to k1, from k1 to k2, and so on, okay, until we get from kt to y, if all those probability distributions they are different from 0, okay, then we say that the states x and y, they communicate, okay. And if the reverse is true, okay, if we can find probabilities of moving from y to x even if we have to do this in a sequence of states, okay, we say that these two states intercommunicate, okay? And if in the parameter space S, okay, all states intercommunicate, then we say that this parameter space is irreducible under this probability distribution Q, okay? Which means that, in other words, we notice here that actually Q, this probability Q, is a moving probability, okay? It's how we move, we make the Markov chain move. Okay. And okay, so and the Markov chain is said to be reversible if the probability of being in state at a state X multiplied by the probability of moving from X to Y is equal to the probability of being at state Y multiplied by the probability of moving from state Y to state X. Okay. And this is a definition regarding the period of the Markov chain. The period is the largest common divisor of that makes the probability of being at a state X coming back to state X is larger than 0. Okay, and the chain is said to be aperiodic if this is 1. Okay. And we say that the chain, I'm sorry, the state is aperiodic if this is equal to 1, and the chain is aperiodic if all states are aperiodic. Okay. And why those definitions are important? Because there is a theorem that says that that the Metropolis-Hastings algorithm, actually, the way that the Metropolis-Hastings algorithm is created, it leads to a reversible chain. Okay. So actually, the Metropolis-Hastings algorithm satisfies this condition of reversibility. Okay. But if the chain is also irreducible and aperiodic, then it defines an ergodic Markov chain with unique equilibrium distribution P. Okay. So that and here that's the point. So this is all very nice, but you see that it has to be irreducible and it has to be aperiodic. And that's the most critical point. Why? Because when you're dealing with physical problems, you know, and you have you're estimating parameters in the mathematical formulation of physical problems, many times those parameters, they are correlated. We have seen here that along the week that we have to take a look at the sensitivity coefficients and examine if the parameters are correlated or not, because if they are correlated, we cannot estimate like a pair of parameters simultaneously. Okay? And when the parameters are correlated, the chain becomes periodic. Okay? The chain becomes periodic. So actually, if the chain becomes periodic, then and the Markov chain being in a stochastic process, this means that all the tools that we use for signal analysis, for a dynamic signal analysis, we apply here for the chain, for the Markov chains as well. But what is the bad side of this? Is that we can only make statistical inference on the samples generated by the chain after we generated the chain. So that's in practical terms, this is the most annoying thing here. Okay, you need to generate a Markov chain, and only after you really have the chain you can do compute the statistics of the samples related to the provided by this chain, by this Markov chain. Okay, so parameters with linear dependent sensitivity coefficients, they generally result on periodic and correlated chains. Okay, and then an equilibrium distribution is not reached. Actually, if the chain is correlated, and a remark is that most of the time we are dealing with non-linear problems, and many times you do a sensitivity analysis based on some local values, but actually when the chain is moving and you are computing the new states, you go to regions that the parameters might be much more correlated than they were before, you know. So we have to this will influence a lot on how to compute the statistics of these chains when we have the correlated chains, okay? But we can identify the correlated chains a posteriori, I mean, after we have the chains, okay? But on the other hand, as I mentioned here, you see, when we do the analysis of the sensitivity coefficients, we identify that the parameters are correlated. In classical methods, you go ahead and you fix one of the parameters that you judge as known. Okay? While here we can provide like an informative prior, I mean a prior with a small variance for the parameters that you consider as known. Okay. So in some sense you're estimating the other parameters, but still taking into account the uncertainties on the parameters that you judge as known, which is something very, very, very good, you know, which is something very good. And an important point is, for example, the sensitivity coefficients. We still need to examine the sensitivity coefficients very carefully to have a successful estimation procedure within the Bayesian framework as we had to do before. Okay, and this has been said. Okay. Okay. All right. Okay. So this the Metropolis-Hastings algorithm. Okay, it actually draws samples from a candidate density, like in the acceptance rejection sampling, which is a classical method in statistics. Okay, so let's say that we want to generate samples from this density P, which is this density P tilde divided by K. And this normalizing constant K might be unknown. Okay. So this is exactly what we have in our case where the normalizing constant of the posterior distribution is not known unless we perform that integration in the space of parameters. Okay. Okay. So instead of sampling from P, we sample from another candidate density HP. Okay. Such that HP multiplied by C by some constant, okay, is always larger or equal than P tilde. Okay. So we take these steps. Okay. We generate a random sample P star from this density H. Okay. And then we generate a uniform random. A random number from a uniform distribution between 0 and 1, okay? And if P tilde, okay, P tilde divided by C H, okay, if U is smaller or equal than P tilde divided by C times H, we accept P star, okay, we accept P star as a sample of P. Okay. Otherwise we do not accept and we continue sampling. Okay. So the idea here is that the idea is that H is a probability function that is easy to sample from, okay? And while P tilde here, okay? It's easy to find the value of the probability function of P tilde, okay? But it's difficult to get samples from P tilde, okay? And it's easy, on the other hand, it's somehow easy to get samples from H, from this distribution H, okay? Okay, and also the Metropolis-Hastings algorithm, it's constructed so that the reversibility condition is satisfied, okay? So this means that the posterior probability at of the parameters at a state t multiplied by this probability function that moves from pt to p star, okay, so generates these candidates p star, this is equal to the posterior probability of p star multiplied by the proposal, this probability that moves the chain from p star to pt. Okay, it's built so that this reversibility condition is satisfied, which of course it might not be always the case, and so it might be the case that the probability of being at pt and moving from pt to p star is larger than the reverse. Okay, so for those cases we introduce a probability alpha which relates pt and p star, okay, so that this condition is always satisfied. Okay, so alpha is actually the minimum of 1 or the posterior of p star multiplied by the probability of moving from p star to pt, okay, divided by the probability of pt and multiplied by the probability of moving from pt to p star, okay. Okay, so we introduced this new probability alpha, okay, and the Metropolis-Hastings algorithm applies the acceptance rejection method over alpha, okay. In this way, it's very simple. It's a very simple algorithm, okay. So we sample a candidate point p star from this proposal distribution, which moves from pt minus 1 to p star. Okay. Then we calculate alpha. We generate a random value that is uniformly distributed on this interval, the interval between 0 and 1. And if u is less than alpha, we accept pt. Okay, I'm sorry. We accept p star as a point of the posterior distribution. Otherwise, we simply make the value of the parameter at the new state t equal to the value of the parameter at the previous state. Okay, and so on. Okay, so it's a very simple algorithm, and of course here we have this. This is the posterior at the candidate point. This is the posterior at the previous state at the Markov chain, and this is the probability that we move from the previous point in the Markov chain to p star. Okay, so this is a probability, the probability function that we generate. We try to generate samples of the posterior distribution. Okay. So, of course, the success of this algorithm, it depends not only on your prior information, but also on the on this proposal distribution, how you move in the Markov chain. Okay. So, but remember the prior is your mathematical representation or statistical representation of your knowledge about the parameters before the measurements become available. Okay. So the point is that you have to code, to appropriately code your information, which many times is only qualitative, in terms of this distribution function. Okay. And so this is very crucial for the success of the problem. As we have seen, it introduces regularization. It provides regularization, but on the other hand, it's biased. Okay, the estimator is biased towards your prior. Okay, towards your prior. And another crucial point here is the selection of these proposal distribution. The distribution that moves along the chain. Okay. Some examples. Okay. Some examples of proposal distribution. Okay. Very simple ones. Okay. For example, random walk. Let's say that P star is equal to, is given by PT plus some vector psi, okay? Where psi is a random vector of random variables with, let's say, with a distribution Q1. Okay? With a distribution Q1. So actually, the probability of moving from P star to PT is equal to Q1 of psi. Okay? Q1 of psi. And if this proposal is symmetric, in other words, let's say that Q1 of psi is equal to Q1 of minus psi, then the probability of moving from PT to P star, okay, is equal to the probability of moving from P star to PT, okay, because here P star minus PT is equal to psi, okay. In this case, when we have a symmetrical proposal, you see that they cancel out in the computation of this parameter of this distribution alpha. Okay, they cancel out, and so alpha is given by the minimum of 1 and the ratio of the posteriors. Okay, the ratio of the posteriors at the candidate point P star and at the previous point PT. And in this case, when we use a random walk proposal with a symmetric proposal, random walk symmetric proposal, it's very clear that when we move towards a region where the posterior is larger, okay, we accept the candidates. Okay, because alpha, remember that alpha is accepted with this probability U, okay, which is a random number between 0 and 1. Okay, so if the posterior at P star is larger than the posterior at the previous state, we accept P star. So this means that whenever we move in the direction of larger posterior, we accept the state. But on the other hand, even if we move in a direction to a region where the posterior is smaller, we still can accept the candidate with some probability alpha. Okay, so this means that this is very nice because then we can explore the state of parameters quite nicely. Okay, quite nicely. And how do we prescribe Q1? Okay, how do we prescribe this the probability of psi? Let's say, for example, that we have a uniform that psi is given by is obtained from a uniform distribution. In this case, let's say for parameter pj, okay, I'm writing here only for one single parameter and not for all the parameters. So the pj star is equal to pjt plus wj. Wj is some maximum variation in the parameter in this movement, okay, multiplied by 2r minus 1, and r is uniform, comes from a uniform distribution between 0 and 1. Okay. Alternatively, we can also use a Gaussian random walk proposal. Okay. We can use a Gaussian random walk proposal where we simply add to pj at state t a random number that comes from a Gaussian distribution with a 0 mean and some standard deviation Sj. Okay, so these are very easily implemented. Okay, these are very easily implemented. Okay, and we can implement them independently for each parameter pj, but this is very simple. Another possibility is to use an independent move. Okay, is to use an independent move. And how do we do this? For example, by sampling from the prior. Okay, you can sample from the prior. Okay, we simply, so it's independent of P of t. Okay, and when you sample from the prior, okay, and when you substitute Q by the prior here, okay, the priors cancel out, okay, and alpha becomes the ratio of the likelihoods. Okay, so in this case, when you sample from the prior, okay, whenever you move in a region to a region that of larger likelihood, you accept the candidate. Okay. And when you move to a region of a smaller likelihood, okay, you can still accept the parameters with some probability alpha. Okay, but see, it looks like the effects of the prior is not taken into account, but actually you are sampling from the prior. Okay, in this case, that you have an independent move. If this can be very nice, you know, independent move can be very nice if you have a very informative prior, in other words, that you have a prior with a small variance, okay? But you have a prior with a large variance, this might be a very bad implementation, okay, of the algorithm. So it might be better, it might be easier for you to actually implement the algorithm with a random walk proposal. And I like these Gaussian random walks. Okay. Okay. And what about the likelihood? Okay. What about the likelihood? So remember that the likelihood, it actually represents your experimental errors. Okay. So the likelihood is your statistical model of your measurement errors. Okay. So this also has to be known. Okay. And can, as I said, can be known from the calibration of your sensors. Okay. Fortunately for us who work in heat transfer, temperature measurements, they are usually Gaussian, but this might not always be the case. An example here is this is actual results that comes from, was done by Henrique here. These are the temperature measurements at a plate, and this plate is at a uniform temperature. Okay, and these measurements, they were taken with an infrared camera. Okay, so each pixel here represents a pixel from this infrared camera that provides local measurements of the temperature. Okay, and this is so this plate is at a uniform temperature. And this is the histogram of all those pixels here. Okay, so we can see that we can fairly approximate this with a Gaussian distribution. Okay, and also, for example, thermocouples, where you take like local measurements of the temperature, they can be fairly approximated by Gaussian. The errors of thermocouples can be fairly approximated by Gaussian distribution. But this might not be the case. Oh, okay, so this is a Gaussian distribution for a parameter Pj, but this might not be. Okay, I'm sorry. This is the likelihood. Okay, and the other ingredient, the prior. Okay, so we have seen an example where the prior was Gaussian. This is the Gaussian distribution with mean mu and variance standard deviation sigma j here, okay, and for one single parameter. And as I mentioned, in this case, you're favoring the values around the mean mu, okay. Which might be very convenient. You might have a good information about these parameters and about the mean mu and how do you get this, for example, from another experiment. Okay. Yeah. So let's see. Okay. And but another point here before we take a look at an important point is that actually. The support of the Gaussian distribution is the real line. Okay, so it's from minus infinity to plus infinity, and we know that many parameters they cannot be negative. For example, physical properties. Okay, physical properties they are usually they are all positive, and so we. This might not be a very good choice for the prior of, let's say, thermal conductivity. And depending on the variance associated with this prior, the probability of getting negative values might be very small. And you might not even have problems in the implementation of the method, but this is not rigorously correct, right? And to have some a probability of finding negative values of a physical property. Okay, so one possibility would be, for example, to use a uniform distribution for the prior. Okay, where we can prescribe the minimum and the maximum values of the parameter. Okay, and all the values inside this interval they are equally probable. Okay, they all have the same chance of being like. Selected, okay, and again, but so this is nice because you can prescribe the bounds, but at the same time you do not favor any value inside this interval, okay. This interval, I mean, the mean is the half of the interval, and this is the variance, and the variance is big because it's a uniform distribution, okay, but on the other hand, you might want to favor some value inside this interval. So, for example, you can combine the Gaussian with the uniform, okay? And let's say that inside this interval between A and B, you have a Gaussian distribution, and then you favor the mean mu, of course, depending on the value sigma j, and let's say that this is 0 elsewhere, okay? This is 0 elsewhere, okay? And so we can provide the bounds, the lower and upper bounds for each parameter. Okay, and so this is a nice prior. Okay, this is a nice prior when you have when you more or less know the bounds for the parameters. Okay, and you can make this truncated Gaussian prior look like a uniform prior if the standard deviation of the prior is large. What I mean is that in this prior, you have something like this, right? You have here. This is mu, so and let's say this is A and this is B, Okay, and then so we have something like this, and what we are saying is that our prior looks like this, right? Okay, so the probability of finding parameters smaller than A and larger than B, this probability is 0. Okay, and we are somehow favoring mu. Okay, and I represented here mu more or less centered, but it does not have to be centered. You only expect that mu is between A and B. Okay. Okay, but if you assume a very large standard deviation for mu, this thing will look like this, right? So you're getting more or less like a uniform distribution inside this interval between A and B. Okay, so if you want to write a general code for this, you may, for example, use this truncated Gaussian, because for each parameter you prescribe the minimum and maximum values and also standard deviation from your prior and the mean, which must be between A and B, and you can then play, because some parameters you might not want to favor any value around any mean. Why? Because this introduces bias. Okay, this introduces bias. Okay, and of course you can have other kinds of distributions as a prior. For example, if you know that, for example, also if the parameters, they are always positive, you can use, for example, Rayleigh distribution. And the Rayleigh distribution, it's very interesting because you have only one parameter to fix it, which is this center point here, gamma 0. Okay, and but on the other hand, while the mean of the Rayleigh distribution is gamma 0 multiplied by square root of pi over 2, the variance is 4 minus pi divided by 2 multiplied by gamma 0 square. Okay, so you might have a very large variance depending on the value of gamma 0 that you prescribe. And you can use, for example, the gamma distribution, which is given by this expression here. So it depends on these two parameters, alpha and beta. Okay, the mean is alpha beta and the variance is alpha beta square. Okay, and but we can, for example, select beta equal 1. So this becomes what is called the one parameter gamma distribution. And but you can also make alpha equal 1 here, and then you get what is called like an exponential distribution. Okay. And this is also for parameters larger than 0. Okay. And another possibility is, for example, to use this beta distribution, which is for the values of the parameters between 0 and 1. But of course, you can adjust this 1 here. And by adding a constant or by multiplying by a constant or both, okay. And but it also depends on two parameters, okay. And how do they look? They look more or less like this, okay. So we have this here. The green one is the Gaussian, okay. The blue one here is the uniform. The Rayleigh distribution is this red one here, so the Rayleigh distribution comes here, okay? It's centered at 0.5. The gamma, I presented the gamma here with parameters alpha and beta equal to 1.5, so this is this distribution here, okay? And of course, you can play with these parameters to have different shapes. And this beta distribution, it's this one here that reaches a peak and goes down here, okay, between 0 and 1. And in this case, they were all normalized here with respect to their maximum value, so we could have everything, all of them on the same graph. Okay, and of course, a truncated Gaussian would be this green line inside this interval between 0 and 1, and 0 outside this interval, for example. Okay. Okay, I'd like to propose to drink a water, drink a coffee, and we come back in 15 minutes. So that's okay. It's okay. And then we are going to see an example. Okay, we're going to run an example. Okay, thank you.